Welcome everyone. During this lecture we will explore the following topics, including the definition of a freely falling or rising body. We'll introduce gravity, gravitational acceleration, and finally we'll derive the freely falling or rising body equations. So what is a freely falling or rising body? It turns out that a freely falling body is any object that is subjected to the pull of the Earth exclusively. There are four conditions that a body must meet in order to qualify as a freely falling or rising body. First, the object maintains no contact with any other object. Second, air resistance must be negligible. Third, there are no active propulsion mechanisms. Such as engines, propellers, etc. Fourth condition, the object must be rising or falling near the surface of the Earth. And there's one more condition, and that is there is no significant spin. We will now introduce the concept of gravity. Gravity is a measure of the attraction that exists between any two masses. by virtue of mass alone. In other words, the Earth doesn't have to be part of the gravity equation. Any two masses have what's called a gravitational attraction between them. Now let's talk about the Earth's gravity. Turns out that the Earth's gravitational attraction toward objects that are near its surface will produce a gravitational acceleration that is independent of the object's mass. This acceleration is given by we're going to call it the acceleration of the Earth's gravity. And it so happens that the value equals 9.8 meters per second squared. And in the British system, the value is 32 feet per second squared. Now the textbooks refer to this value as g. And so g does not refer to gravity. It refers to gravitational acceleration. And we'll make a note of that. So g, if we had to describe it in one word, the word is acceleration, not gravity. G is not gravity, g is gravitational acceleration. And as you can see, the value for g equals 9.8 meters per second squared, or in the alternative, in the British system, it's equal to 32 feet per second squared. Now I'd like to call attention to a very interesting statement within our notes. It reads that the Earth's gravitational attraction toward objects that are near its surface will produce a gravitational acceleration that is independent of the object's mass. In other words, the Earth does not discriminate on the basis of mass. So what does that imply? Well, I would encourage you to conduct the following experiment. Let's say that this is ground level and you're holding a light object such as a coin in one hand and you're holding something heavier like a textbook or a shoe or a baseball in the other hand. If you release both of these objects at the same time from the same height, you will observe that the coin and the baseball will reach the ground at exactly the same time, despite the fact that the baseball is much heavier than the coin. We will now introduce the freely falling or rising body equations. And in order to derive these equations, we just need to observe that a freely falling or rising body is just an object moving in one dimension. It's not moving along the x-axis, it's moving along the y-axis. This is vertical motion, and so what we need to do is just basically recycle the one-dimensional motion equations and adapt them for vertical motion. And we'll do that by introducing the following substitutions. Instead of x, we will substitute y into the equations, and instead of a, we will substitute negative g. Remember, g refers to gravitational acceleration. So here are the one-dimensional motion equations. I have a small box that contains them. You don't need to copy them. You already have them in your notes. And here's what we'll do. Let's take a look at equation number 1. It reads v equals v0 plus at. What we'll do is we will remove the a and substitute negative g in its place. So the first equation looks like this. V equals v0 minus gt. In equation number 2, we'll substitute y for x. So now equation number 2 reads as y equals average velocity times time. Equation number 3 has no changes whatsoever, and so we'll just reuse it as v0 plus v over 2. Equation number 4 looks like this. X equals v0 plus v over 2 times t. We will substitute y in for x. So this equation looks like y equals v0 plus v over 2 times t. Equation number 5, you can see that the only substitution, actually there are two, the acceleration will be substituted by negative g, and x will be substituted by y. So this equation becomes v squared equals v0 squared minus 2gy. And finally, in equation number 6, the x becomes a y and the a just becomes negative g. As a result, equation 6 looks like y equals v0t minus 1/2 gt squared. So we'll wrap this set of equations up in a blue box as well, and we'll label this as the freely falling body equations. And of course we recognize that they apply to rising bodies as well. And we will also note the following observations. First of all problems must begin at y equals 0. What does that mean? It means, let's say we have an example where a ball is thrown from the ground. The ground level will be defined as y equals 0. On the other hand, if we're throwing a ball from a rooftop, the rooftop is now defined as y equals 0. And let's say that the building is 50 meters in height. What that implies is the rooftop is considered to be y equals 0, and the ground would be considered to be at y equals negative 50 meters. because the ground is below where we started, and we'll emphasize this in our next example. The next note states that upward motion is indicated by a positive velocity. In other words, v equals positive whenever the object is moving upward. And likewise, downward motion is indicated by a negative velocity. In other words, v equals negative whenever the object's moving downward. Here's something very important. When an object reaches its maximum height, its velocity must equal 0. In other words, v at max height equals 0. And the final observation is that y refers to the object's coordinate. And not the distance traveled. We will now introduce an example that demonstrates the usage of these equations. So in this example, we have a ball is thrown straight upward from a rooftop with an initial velocity of 30 meters per second as shown below. The rooftop's height is 75 meters and the ball just misses the edge on its way down toward the ground. We need to determine the following for this example. Now, let's first of all note that the ball starts off with an initial velocity of 30 meters per second. In order to illustrate that, we will introduce some speed lines and indicate that the ball does have an initial velocity, which we'll call v0. Also, if you recall, we had a statement that noted all problems must begin at y equals 0. So what we'll do next is introduce the x and y Cartesian coordinate system. So we've identified the y-axis, we've also identified the x-axis, and notice that the intersection is defined as 0, 0. And so the question now is, when the ball reaches the ground eventually, can you tell what the y-coordinate will be? Well, if the building is 75 meters high, the ball will be 75 meters below the x-axis, and of course we know that any location below the x-axis means that the y-coordinate is negative. In other words, the answer to the question is the y-coordinate of the ball when it reaches the ground is negative 75 meters. Now, in part A, we're asked to find the time required for the ball to reach its maximum height. Let's draw the ball at maximum height. So let's assume that the ball rises to this level right here. We also noted in our observations that when an object reaches its maximum height, its velocity must equal 0. So v at max height equals 0, and we'll note that in our diagram. So the velocity at this location which is maximum height, equals 0 for the ball. And in part A, again, we want to determine the time required for the ball to reach its maximum height. So let's go about solving this. We want to find t for y max. Here's what's known in the problem. We know that the initial velocity, v0, was given in the problem as 30 meters per second. We also know that the velocity at the location that we're interested in equals 0. With these two values, we should be able to determine the time for maximum height. So let's take a look. We know v0, we know v, now we want to find an equation that solves for time. In the first equation, there is a time, and we do have a value for v. We know the value of v0, and g, by the way, is always known. The value for g in our equations is always 9.8. And by the way, we always introduce it as 9.8 and retain this negative value. We don't introduce it as a negative 9.8 and cause a double negative. Let's keep that in mind. So this is our equation, and let's apply it now. Here it is. V equals v0 minus gt. For v, we'll insert a 0. v0 equals 30. G, like I mentioned earlier, is 9.8 times time. How do we solve this algebraically? First of all, we'll transfer the 9.8t to the other side, and it's going to change its sign. So it's negative on the right. It becomes positive on the left. And if we solve this by dividing both sides by t, we obtain a value of 3.061 seconds. And we'll note that this is the time required to reach maximum height. In part B, we would like to determine the maximum height. And of course, that will be determined through a calculation of y max. So again, based on what is known, let's find an equation that will solve for y max. Alright, the first equation won't do anything for us because there is no y term contained within it. The second equation won't work because we don't know the average velocity in this problem. Let's go to the fourth equation. Here's y. We do know v0. We do know the final velocity at maximum height, of course, that equals 0. And we just found out the time to reach maximum height. This is the equation that we'll be using. So, y equals v0 plus v over 2 times t. Let's substitute the values. v0 in this problem is 30. The final velocity at max height is always 0. And the time we just found out equals 3.061. And if we enter those values into our calculator, y max will equal 45.92 meters. Of course, this is 45.92 meters above the rooftop, and I'd like to note that. If we had to determine the height above the ground, we would actually have to add 75 meters to this value. Now, in part C, we want to determine the ball's velocity when it returns to the rooftop's level. So in other words, we have to draw a third location for the ball. The ball is now over here, and it is traveling downwards. Again, it just missed the edge of the rooftop on its way down, and we would like to find the velocity of the ball right here. Well, we have to determine what is known here. And can you tell what is known? Do you know, for instance, the velocity of the ball at the rooftop? Well, we don't know the velocity. What we do know, by the way, is that the y-coordinate of the ball is equal to 0. Again, we are crossing the x-axis, and of course the y-coordinate of the x-axis is 0. So we'll indicate that at this location, we know that y equals 0. So with that, we'll be able to find the ball's velocity when it returns to the rooftop. Level. So let's take a look at our equations. Here they are. We want to determine velocity, and the first equation will not work for us because we don't know the total time that it takes the ball to return back to the rooftop. And we can't assume that it's double of the time required to reach maximum height because we haven't proven that. This equation cannot be used either because we don't have average velocity. This equation, again, relies on time. Equation number 5 is interesting. Let's take a look. It has v, which is what we're looking for. We know the initial velocity. We always know the value for g, and we just established that the y-coordinate at the rooftop equals 0. This is the equation that we'll be using. So the equation is v squared equals v0 squared minus 2gy. Let's see what happens. So we're trying to solve for v. v0 equals 30. We'll square that. Minus 2. G is 9.8, and as we noted earlier, the value for y is 0. So this just produces v squared equals 900. Now, algebraically, we have to take the square root of both sides in order to solve for v. Now, if we take the square root of v squared, that produces v. And if we take the square root of the other side, we're obligated to place a plus and a minus in front of that radical. And so our result is plus or minus square root of 900 is 30. The question is, should we choose the positive velocity or the negative velocity? Well, we know from the problem, let's take a look for a moment, that the ball is on its way down when it reaches the rooftop level. And so because of that, we must choose the negative. And again, that's because the ball is traveling downwards. And so our answer is v at the rooftop level just equals negative 30, and the units for velocity are meters per second. Let's take a look at part D now. In part D, we're asked to determine the ball's total time of flight. So in other words, we want to know how much time has elapsed between the initial point and the time when the ball returns to the ground. Now, we're going to draw the ball now at that location. Here it is. And we'll note also that in order to use our equations, this ball is not allowed to come into contact with any other objects, including the ground. So we'll find the time of flight and associate that with the ball's location just before it hits the ground, the microsecond before it hits the ground. And so we want to indicate that the ball has not reached the ground by introducing speed lines. That shows that the ball is still in motion, and that means that we're allowed to use our equations because we haven't violated the conditions. Again, the ball is not allowed to come into contact with the ground. Now, if it's not in contact with the ground, it means that it's still moving, and therefore we can't introduce a value of 0 for velocity at this location. So the question is, what do we know about this location? In order to use our equations, we have to feed information to them about specific locations. So does anybody know what we know about the ball at this location? And it turns out that the answer to that is we have knowledge of the ball's location. It is located right now 75 meters below the x-axis, and so we can note that at this location, y equals negative 75 meters. Now we need to identify an equation that'll solve this problem for us. So we're looking for the total time of flight. Can we use equation number 1? And the answer is no, because we don't have knowledge of the velocity when the ball is about to strike the ground. This one has time in it, equation number 2, but we don't know the average velocity. Again, we have equation number 4, but we don't know the value of the final velocity just before we reach the ground. Equation number 5 has a reliance on velocity, so we can't use that. This is our last chance. Equation number 6, let's see if that'll work. We do know the y-coordinate just before we strike the ground. We know the initial velocity. We always know the value of g. This is the equation that we'll be using. So again, in part D, we want to determine the total time of flight. And we've determined that this equation will solve it for us. Y equals V0t minus 1/2 gt squared. Let's substitute what we know. We know that the y-coordinate of the ball just before it strikes the ground equals negative 75. The initial velocity was known to be 30. Of course, g just equals 9.8 times t squared. And now we're faced with another issue. How do we solve this type of a problem? Well, if we look back to our algebra knowledge, we'll recognize that this pretty soon will look like a trinomial. And in order to solve for this trinomial, we will have to apply the quadratic formula. All right, so here's what we'll do first. Let's simplify this a little bit. Of course, 1/2 of 9.8 is just 4.9. What I'll do next is, in order to use the quadratic formula, we need to have everything on one side and a 0 on the other. So what we'll do is we'll transfer the 30 over to the left-hand side. We'll also transfer the negative 4.9 to the left-hand side. And here's what we get. Notice that whenever we transfer a term to the other side, the sign has to change. So the 30 became a negative 30, the negative 4.9 became a positive 4.9, and the 75 stayed on the same side, so it retained its sign. Now, in order to solve this, again, we need to rely on the quadratic formula. Let me introduce that. The quadratic formula from algebra looks like this. If we want to solve this for t, it equals negative b plus or minus the square root of b squared minus 4ac on top of 2a. Of course, the a, b, c are located right here. The 4.9 is A, the B equals negative 30, and C equals negative 75. So let's introduce them into the formula. So we have a negative 30. We have a double negative there. Plus or minus negative 30 in parentheses. When you square that negative 30 on your calculator, we have to introduce parentheses around it. Minus 4. The value for A is 4.9. And C equals negative 75 on top of 2 times A. That leads to negative 30 is just positive 30, plus or minus. If we conduct the calculation inside of this radical, the value that results is 2370. Keep in mind that we have a negative and a negative here, which really cancel to be a positive on top of 2 times the 4.9. And that results in 30 plus or minus the square root of 2370 equals 48.68. 2 times the 4.9 is just 9.8 in the denominator. And now we have to make a choice. We're either going to choose the minus or the plus. Now we're not going to choose the minus because that would produce a negative value for time, and there's no such thing as negative time. And so because of that, we'll choose the positive result. And so we advance the problem by noting the positive choice. That leads us to 78.68 on top of 9.8. And finally, the time of flight equals 8.029 seconds. And that completes this lecture.